says the Bronsted Lowry worksheet, and let's get started on this. You should try to answer these and do some of these and then check. I know that's hard when I'm here because I can't give you wait time. So let's get started. First, we're asked to write the formula for a proton. And the formula for a proton in this context of this unit will be H+. Remember that we talked in class about a proton can be a hydrogen atom that has lost its electron. And a hydrogen atom that's lost its electron has an H+. Our second question asks us, what is a hydrated proton? Remember, hydrated means it has a water on it. So if I have an H2O that becomes hydrated, the H2 becomes H3O, and it's a +1 charge. That's the answer for number 2. Number 3 asks us to write the formula for the hydronium ion. If you'll recall our notes from yesterday and your reading, the hydronium ion is H3O+. Next, we're going to look at the Arrhenius and Bronsted definitions for both acid and base. The Arrhenius definition of an acid is an H+ donor. An example would be HCl or H2SO4. Remember that the Arrhenius definition is the narrowest or most restrictive. So that's the most restrictive classification. The Arrhenius definition of a base is an OH- donor. So it's restricted to metallic hydroxides. Examples would be sodium hydroxide or perhaps magnesium hydroxide. The Bronsted definition is a broader definition, but you'll notice that the Bronsted definition of an an acid is the same as the Arrhenius definition. It's an H+ donor. The Bronsted definition of a base would be an H+ acceptor. I want to make a note that Bronsted Lowry acids and bases, these two, exist in pairs. And they have, the acid has a conjugate base and the base has a conjugate acid. Now let's look at the substances we have right here. First, I'm going to look on the left side. Then we will discuss what's on the right side. So looking at the two species that I have in yellow, we're going to identify which is the acid and which is the base. And this is going to be under the Bronsted-Lowry definition. So the acid on the left will be, you can pause now if you want while you think about it, will be H2S. H2S between here and here, you can see that it donates an H+. It is therefore the acid. The base is HCO3-, And you can see that from here to here, it accepts an H plus. I'm going to slide over a bit. Now the acid on the right side, we're going to look at the right side now. So we're going to look at the two species here. Sorry about that. H2S. So now we're going to look at these two species. The acid of those two, remember, is the donor, and that will be H2CO3, which is carbonic acid, which leaves as my base HS minus. Now, above these, and I'm going to try to make this bigger so you can see what I can doing, I'm going to write acid, and I'm going to write base. Now, this is my conjugate base, and this is my conjugate acid. It's my conjugate base and my conjugate acid. Next, we're asked to find the conjugate acids of each of the following that we have right here. And I want to make a note that in order to find our conjugate acid, we're going to add a, or one, hydrogen. So to the monohydrogen phosphate, we're going to add one hydrogen. And that will now have a 1 minus charge. So that'll be the dihydrogen phosphate ion. Next, let's do B. PO4, 3. Let's add one hydrogen. Oh, look, it becomes this one. How interesting. Now, let's add a hydrogen to HSO4, and we'll get H2SO4, sulfuric acid. 2 left. Let's add a hydrogen. The ammonia will become ammonium. And finally, my dihydrogen phosphate, which is what I had right here, will become phosphoric acid when I add. What I've written here is the conjugate acids of each of the following. So the acids are these, and the basis for those pairs are the ones in blue. Now our next thing is we're going to draw, or write, not draw, I guess. We're going to write our conjugate basis. For these, we are going to take away or remove, a hydrogen. So here we're going to remove a hydrogen. Our H2PO4 will become HPO4 2 minus. B will remove a hydrogen. Removing a hydrogen, that will become sulfate. I'm not doing these other two for you. Oh, I suppose I better do this one. If I remove a hydrogen here, this becomes OH minus. I'm not going to do that last one. Next, we are going to give the formulas of a conjugate acid-base pair in which dihydrogen citrate is the conjugate base. Dihydrogen citrate is the conjugate base. So I'm going to tell you that dihydrogen citrate, whoopsie, writing in the wrong spot. Dihydrogen citrate is H2 C6 H5 O7 minus. That is dihydrogen citrate. Now, if we read the next problem, we can see that the dihydrogen citrate has to be the conjugate acid. So I'm going to write the same formula here. Now let's write this as a conjugate acid. So to write a conjugate acid, we are going to add a hydrogen. There'll be no charge there. And to write the conjugate base, we're going to take away a hydrogen. And this will now have a 2 minus charge. Then is dihydrogen citrate amphiprotic or amphoteric? And the answer is yes, because it exists as both an acid and a base. So yes, it is amphoteric. So I'm going to write can act as an acid or a base. For this one, I'd like you to write 3 amphiprotic anions. Anions have a negative charge. You may look these up if you want to. Go ahead and name them. Do I have 3 on here? I feel like I had 4 on there. Oh well. So this next part is sort of hard, and you could probably find some people to argue this. But the strongest acid that can exist in aqueous solution is H3O+. And you might guess the strongest base that can exist is OH-. So now we're going to look and see which would have the higher hydronium ion in water. And we're given two different concentrations of the same acid. Make sure you know that this is perchloric acid. Good heavens, I've been doing this forever. And obviously we're going to pick the one with the higher concentration. Next, I have 2 strong acids here. No, I don't. I have 1 strong acid. This is a strong acid. This is not a strong because it's nitrate, so it'll be this one because they're the same molarity, which would have, with the higher concentration, the iodic, 1 molar iodic or 1 molar sulfurous. I believe it's this one. And that would be based on, we'd have to look up the Kas for these. I'm thinking. So I think on these you're going to have to start looking up some Kas on these. Let me make a little note. And you can just find a table. Just type in table of Kas. And you're going to find some that you even have 2 for. You might have Ka1 and Ka2. You'll just have to see what's happening. So you can go look up those two Kas. You can see that they're both the same value. I'm going to go through and tell you which one you should be looking at. And then you can go see the strengths of these. Oh, this one, HPO4 or H, I think it's this one. And I think it's these two. Now you're going to have to probably go on into our next section for all of these that I've been doing from here on. Actually, maybe here. You'll probably have to get a little of the next lecture. So weak acids and strong acids, in case you want to stop, you can feel free. First, let's go ahead and see if we have any strong acids here. And I've got, here's one. Here's a strong acid. Perchloric acid is a strong acid. And let's see, this is a weak acid. This would be the ClO4 would be a spectator ion probably. You have any other spectators? Cl is often a spectator because it is, for a spectator, where's spectator? This is the anion of a strong acid. So I think those are the only two. And a weak acid. I've got a weak acid. So F will be a weak base because this is a anion of a weak acid. The HiO3 will be a weak acid. This will be a weak base. Ooh, does this look like a... That's going to be a spectator. My O2 minus, I think that's going to be a strong base because it is an oxygen. And then my oxalate, I think will be a weak base because it is the conjugate base of a weak acid. Okay. Next, let's do a couple of these, and these are going to be hard right now. So we're asked, what is the OH concentration, of a solution that's made by adding that many moles of calcium oxide, to 500 mils of water. Let's do this. I do tell you to be careful. So I'm going to write down my dissociations for each one of these. Calcium oxide will dissociate into calcium and oxygen. The oxygen will further dissociate, The oxygen, which will be an aqueous solution then, is going to break down as follows. So I can see that each one of my oxygens, I got to get this balanced here. Each one of my calcium oxides has two hydroxides. So let me go ahead and do this. Remember that molarity equals moles per liter. But I'm going to have to do a second mole calculation. I'm going to do my mole calculation up here. I'm going to write a factor. 1 mole of calcium oxide produces 2 moles of OH minus. And we've proved that with this equation right here. So when I'm looking at my moles, I'm going to have to take my, where's my value? 0.060. I'm not leaving myself enough room. Let's switch colors so you can follow what I'm doing. I'm going to write it right here, and then I'm going to have to erase it. 0.060 moles of calcium oxide produce 1 to 2 moles OH minus and calcium oxide. You can see that the value of this will be 0.120 moles divided by 0.500 liters, which will equal, good heavens, I just don't ever leave myself enough room here. This will equal 0.24 molar. The answer for our first one is 0.24 molar. Take a look at that and make sure that calculation makes sense. Remember, I asked you for the OH concentration. Now I need to erase a little bit because I got stuff in the way here. Let's do one more. Then I'm going to quit doing this because it's too hard to upload giant videos. For this one, we're asked what the H3O plus concentration is when we add this many moles of nitric acid to this many milliliters of water. This one will be much simpler. This is HNO3, which is a monoprotic acid. So that it'll be a 1-to-1 ratio of this. So 1 HNO3 is equal to 1 H plus as far as moles. Mole. So my moles will actually be 0.020 moles divided by moles of H plus divided by 0.5000 liters, 0.040 molar. Okay. Now these next pieces I don't want you to worry about right now. I think those are going to be a little too hard for you. See what else I have here. Oh, let's look at this one right now. Let's look at 37. There's a KEQ of HA2. Let's look at this one. I haven't decided this is a good idea or bad idea. So here is a balanced chemical equation, and we're told that the KEQ is this. So let's go ahead and label our acids and bases. For this one, our KEQ is low, so we're going to have our reactants are favored, which means we're going to have a weak acid and a weak base. Let's take a look here. Which is the stronger conjugate acid and which is the stronger conjugate base? Okay, so this is going to be an acid with this KQ. It's going to be a weak acid. This is going to be a weak base, which means this is going to be a strong acid, and this is going to be a strong base. Which is the stronger conjugate acid in the above equation? I will go HCD. And which is the stronger conjugate base? SB. Now let's look at the next equation. Here we have our acid and our base, and we have our KEQ. So our KEQ strongly favors products. So this is going to be a strong acid and a strong base. So this is going to be a weak acid and a weak base. So which is our stronger conjugate acid? If it's going to be, it'll be our stronger acid, H2X, and our base will be YZ minus. So equilibrium always favors the weaker acid. Now some people might want to think this. That means in a strong acid, all the strong acid turns sterns. I should write dissociates. So the equilibrium shifts away from a strong acid. Obviously, that's why it favors the weaker. And then again, it favors the weaker base. And some of those you might want to mess around with, but I've got an answer key for the rest of these. That's enough of this one. You can take a few minutes, look at this, check the answer key. Again, I want to mention that once you get down to this part, right in here, you need to get some equilibrium talks here. And if you look, it does say Bronstead acids and equilibria. So, hope you got something out of this.